Hello again, ladies and gentlemen. Mr. Donahue here. Going to go over some molecular empirical formulas, converting between the two. What are they? Why are they important? How do we go from one to the other? All right. So first thing, what the heck are they? So molecular formulas are basically they just show you exactly how many of each element are in a molecule. So for example, you may be familiar with this one, C6H12O6. That's sugar. It's saying in each molecule we have 6 carbons, 12 hydrogens, and 6 oxygens. Right? The empirical formula shows the ratio of each element in a molecule. Essentially, it's a simplified version of molecular formula. So we would just take C6H12O6 and go, all right, well, I see that they have 6 in common with all those numbers. I can divide everything by 6, and I would get CH2O, which coincidentally is why they call it a carbohydrate, because you have 1 carbon with each water in the formula. That's why they call it a carbohydrate. So why do we use the empirical formula if the molecular formula tells us everything about the molecule? All right, it seems like the molecular formula would be better because it tells us exactly what's in the molecule. The reason is because in experiments, you can't directly get the molecular formula. You can't find out exactly how many of each element is in the molecule, but you can find out the ratio between them, right? So for example, scientists might say, so we broke a bunch of these molecules down, found that for every hydrogen, there was 1 oxygen. It could be HO, it could be H2O2, it could be H3O3, or so on and so forth. We don't really know, but we know that it's a 1-to-1 ratio. So this is kind of like what's happening. So here I drew, or I didn't draw, but here's pictures of the molecule, right? We can't look at the molecule itself because we are not the magic school bus. We can't shrink down to the size of molecules and see what's going on. But we can break them apart and see how many of each element we got. We can break them apart and separate them. So boom, we broke them apart. We separated the hydrogens from the oxygens, and you can see it's a 1-to-1 ratio. All right, well, that again tells us it could be HO, it could be H2O2, or it could be H3O3. We don't know from this information, but we do know the ratio is 1-to-1. So experimentally, we can find the empirical formula. So going from the molecular to empirical formula is probably the easiest thing that we'll cover in this video. Basically, you're just going to find the greatest common factor and divide each number by it. So if this was my formula, C6H12O6, well, I know that they both have 6 as a common factor. So I can divide each number by 6. So C6, divide that by 6, you get 1 carbon. H12, divide that by 6, you get 2 hydrogens. And O6, divide that by 6, you get 1 oxygen. So the empirical formula would be CH2O. All right, so a little practice for determining the empirical formulas from molecular formulas given. So if we have C6H6, you go, well, hey, I can divide each thing by 6. The empirical formula would be CH. Here's the example that we've done already. Sugar, C6H12O6, would simplify to CH2O because you can divide each thing by 6. N2O4. All right, well, 2 and 4 shares 2 in common, so I can divide everything by 2. I'd get 1 nitrogen and 2 oxygens. CH4, well, it's 1 and 4. There's not much I can do for that. So it turns out that this empirical formula is also the molecular formula, which can happen, right? So in the molecule, we have 1 carbon and 4 hydrogens. That's also the simplest whole number ratio. So the molecular formula is also the empirical formula. Next one, we got C2H4. They both share 2, so divide each of them by 2, and you get CH2. H2O2, well, there's 2 hydrogen, 2 oxygen. That would simplify to be HO. C4H6, well, what does 4 and 6 have in common? 2. So I can divide each thing by 2, and I get C2H3. Can't simplify that anymore because we got 2 and 3. We can't do anything about that. P4O10. Well, we got 4 phosphorus and 10 oxygen. All right, 4 and 10 share 2 in common. So I can simplify that to P2O5. And that's as simplified as I can get it. So I move on to the next one. C2H2. Well, this is another kind of easy one. They're both 2, so I can simplify that to CH. All right. Oh, hey, look, it had the same empirical formula as C6H6. Crazy. NH3, Can't simplify that anymore, so the molecular formula is also the empirical formula. Okay, so how do you go from empirical formula to molecular formula? Well, you'll need to know two things which will always be given in the problem. All right, you need to know the empirical formula and you need to know the molecular weight. And they'll tell you both of those things in the problem. So what do you do with this information? Here's an example. A hydrocarbon has an empirical formula of CH2 and a molecular mass of 28 grams per mole. What is the molecular formula? Well, if we have CH2, the first step is, well, how much does the empirical formula weigh? What is its mass? What is its GFM? Well, I know carbon's 12, each hydrogen's 1, so I found that it has a GFM of 14 grams per mole. Now, the empirical formula is telling us that it's always going to be in this fixed ratio. It's going to be CH2, or it's going to be C2H4, or it's going to be C3H6. Either way, we're going to keep increasing it by a factor of CH2, which means we're basically counting the mass by 14s, right? This would have a mass of 14. C2H4 would have a mass of 28. C3H6 would have a mass of 42. If I can do that math correctly, right? So it's going to be some sort of multiple of 14. So the next step is going to be figure out our multiplier. You're going to look at what the molecular mass is, and you're going to go, all right, well, the molecular mass is actually 26 grams per mole, and the mass of the empirical formula should be 14 grams per mole, which I figured out by looking at the empirical formula. So that's telling me, well, if I'm counting by 14s, I must have 2 of those. So I look at my formula. Well, if I have 2 CH2s, the molecular formula would be C2H4. So it just times the empirical formula by that multiplier. Let's take a look at a couple more examples. Hydrocarbon has an empirical formula of CH and a molecular mass of 78 grams per mole. What is the molecular formula? Well, first step is, well, what is the mass of CH? Carbon's 12.0, hydrogen's 1.0. I add those together, and I get 13.0. So I know that this is what I'm counting by. I'm going to go 13, 26, so on and so forth. So how do I figure out how many CHs do I have? How many empirical formulas do I have in the molecule? Well, you take the 78 grams, and you divide it by the 13, and you get 6. So now you know you have 6 CHs in your molecule, which means the molecular formula would be C6H6. Take a look at another one. Compound is an empirical formula of HO and a molecular mass of 34 grams per mole. What is the molecular formula? Same process. So HO, I know H is 1.0 and oxygen is 16.0, so I know that I'm counting by 17s. So that is the mass of my empirical formula. Now it's saying the molecule is actually 34. So I do 34 divided by 17 to figure out how many empirical formulas do I have in my molecule. That's 2. So the formula will be H2O2 because I just doubled my empirical formula of HO. Another example, a compound has an empirical formula of CH2O and a molecular mass of 80 grams per mole. What is the molecular formula? So I got to take a look at CH2O. Carbon's 12.0. I get 2 from the 2 hydrogens plus the 16.0 from the oxygen. And I get, oh man, this was a typo, huh? Yeah, I get 30 grams per mole. So if you're following along in your nose packets, change that 80 to a 90 grams per mole. All right, my bad. Just stop yelling. You don't gotta yell. All right. So now you do 90 divided by 30. That gives you a multiplier of 3. So we know we have 3 of these guys in our molecule. So our molecular formula would be C3H6O3. Right? We can check this too. If we're feeling crazy and we're like, hey, this is weird, let me check it. All right, so I got 3 carbons, which is be 3 times 12, plus 6 hydrogens, which would be 6 times 1, plus 3 oxygens would be 3 times 16, right? And now I can check and make sure that that has a molecular mass of 90 grams. And sure enough, it does. And I can also check, well, let me simplify this, and I should still get my empirical formula. All right, I can divide everything by 3, and I'll get CH2O. Awesome. One last example. Compound is an empirical formula of NO2 and a molecular mass of 92 grams per mole. What is the molecular formula? Same process. Well, I know if this is my ratio of NO2, I look up nitrogen, which, oh man, is it 14? I think it's 14. Plus 2 oxygens, each are 16. And I get, that's 32 plus 14, I get 46 grams per mole. All right, well, how many NO2s do I have if my whole molecule has a mass of 92? Figure that out. I do the 92 divided by 46. I get 2. So I must have 2 NO2s. So my molecule should be N2O4. So what I'm doing is I'm just doubling this, right? I'm doubling that. That's it. All right. And I think I'm going to start leaving you guys with some comics. I'm a big fan of XKCD comics. They're funny. You know, check out the website. They got some hover over text that makes them even funnier. Some of them are kind of, you know, well, I don't know that specific topic, so it's not funny to me. But if you click on them, you can find Explain XKCD, and it'll explain the joke to you, and then you can laugh. All right. So hope you found this funny. I'll see you in class.